Hello, Atomic Physics number 9, Nuclear Stability. So in this one we're just going to again very quickly recap some of the stuff that we've already talked about in physical science a year ago, as to why some nucleuses or nuclei are stable and others have to decay through alpha, beta and gamma decay. Bring you up to speed with one terminology phrase is transmutations. That's when atoms undergo radioactive decay. So a transmutation is an atom undergoing alpha, beta or gamma decay, or being bombarded by neutrons or protons. Anything where there's a change in the nucleus of an atom is a transmutation, basically. Now, why do they decay? Well, they decay basically because the nucleus is unstable, has too much energy. And we'll see why, but basically it's the neutrons, they apply what's called the strong nuclear force, and that overcomes the electrostatic repulsion of the protons. Now that's not a problem with the smaller nuclei, because there's not many protons and there's a pretty much even number of neutrons, and so they can apply the strong nuclear force quite well. As the nuclei or the elements get heavier, and they get more and more protons, you need more and more neutrons, and it becomes a swirling mass of instability, and so it decays and tries to realign itself with a more stable form. Ideally, the ratio of neutrons to protons should be about 1 for the lighter elements, and then as you get heavier, there's it departs from that ratio. So if we looked at something relatively light like oxygen, it has 8 protons, 8 neutrons, and it has the ratio 1 to 1. But as we get progressively heavy, so this is 65, 207 for lead and 238 for uranium, you can see that the number of protons is increasing, but the number of neutrons is increasing at a much faster rate to try and keep that nucleus together. And the ratio is changing and getting larger and larger, and we can see that on a diagram where this is the number of protons, this is the number of neutrons, and ideally it's a straight line up to about here, and then it starts to depart, and you can see a curve there. And we've got another diagram that shows this here. See, it's following, I think they've got this around the other way, yep, because it's bending down rather than up. And there's our stable nuclei, this band here, and you can see it's approaching 1.6 for the heavier elements. And we'll talk about this a bit more when we look at fission and fusion as well. And we've mentioned also this in terms of stability, in terms of the binding energy, haven't we? So it's all coming together, hopefully. Now, this is a diagram out of New Scientist. It's basically showing, again, I think if we go back one, it's the identical. So we have neutrons and protons. So neutrons are increasing this way, and protons are increasing that way. And the black band is the stable nuclei. And if you can see this, we're going to go to a bigger view of it shortly. Basically, this is the half-life of the nucleuses, and so very small half-life there to much longer half-life up to a year or more. And so you can see that as you move away from this stable band, you become less and less stable. Now, this is what we're showing here. So if we actually go to the web page, oops, here we are. Alright, I should be able to. Now if we zoom in on the lower bit here, we start with hydrogen and helium. Now the thing I wanted to point out here was there are things called magic numbers. So you may think that only the elements in the black are stable. However, there's these things called highly stable magic number nuclides, and that's where these red lines cross. And so something like just there and there are very stable, but they don't have to be just in the black. Here we have a cross here, there we have one there, and there, and so these elements sit outside this band, but for one reason or another, neutrons and protons can arrange themselves to be highly stable, and so they're sort of like outliers basically. What else do we need to know? Now, we're also pretty familiar with this diagram in that if you have your parent, if it undergoes alpha decay, it jumps down 2. If it undergoes beta positive, it goes that way, beta negative that way, single proton, 2 proton. So you can get decay series, and when we talk about decay series, we'll look at this in a little bit more detail. Now, the other thing this diagram shows is if you're on this side of the black line, you have an excess of neutrons and tends to lead to beta minus decay, and if you're on this side, you have an excess of protons, which tends to lead to beta plus decay. And that should, when we do the next topic, that should make a bit more sense as well. And that will do us. Let's go back to the PowerPoint. Okay, and in the next video we're actually going to look at radioactive decay, so it may make a bit more sense as well.